treat the galaxy as one big point and work out the gravity on that. So yes, you can do that. But if you want to know how that isolated galaxy formed, then you have to model everything. You have to model gas falling in, you have to model stars forming from the gas, you have to model black hole. Then it becomes complicated. It's as complicated as doing the simulations that I just described for you.
And just one more question.
Sure.
You also said that AI has been making, great leaps, has been helping a lot in the physics. From what I've understood of AI, I've seen it basically is just a more elegant form of computation. But at the end of the day, it uses previous data to make new data. But since the previous data that we have is basically just the laws that we already know. How is AI helping us make new data that we don't know? Isn't it using the same data that we already have?
Actually, that's an excellent question. So let me give you an example of something that we know how it behaves, but we have no good theoretical understanding of how to explain it in detail. Turbulence.
Right.
So if I take water, in a glass and I swirl it, or if you watch the river as it moves and it's churning, especially if it's falling over rocks, it's churning around, or if you go to the ocean and you look at it, that behavior of water churning around, we understand it, but we don't know how to describe it in detail. It's very complicated. That's the problem. Now, what happens with AI, especially in the case of turbulence, is that I can either do simulations, but it turns out that the simulations of the kind I do is not enough. I need to have simulations that cover the big scale, it's like covering the entire scale of this room.
Zooming out.
And I should be able to zoom in to tiny little details to the size of a molecule. But I can't do that. I just don't have the computing power to do that. Okay? But what I can do is I can train an AI. Now you say it's an elegant computing system, but it's actually a little bit more than that. An AI can figure out patterns and make inferences from those patterns where we get stuck with the statistics. So statistically, there's no difference between model A and model B. But AI can figure out tiny little differences and pick it up and basically magnify it. And so using that capacity to figure out what the arrangement is in a complex system, and then if I train it, I have to train it on numerical simulations. So I have lots of simulations, I train it, it learns about turbulence. I don't know how to predict it, but it figures out how to predict it. So then when I say, okay, here's the input, tell me what will happen, it will take a good guess. And the guess, if you train your AI smartly and well, the guess is better than the guess I will make. That's the thing. There are certain things that are so complicated that we can't calculate ourselves. But somehow, the way it's structured, it can extract that information out.
Thank you, sir.
Yeah.
Do all galaxies have black holes?
All
Galaxies have
Yes, all galaxies are black holes.
Sir, I have two questions. The first question is regarding galaxies that you observed. And you said that blue is colder and red is warmer. Now, they're also moving away from us. So there's a redshift. Now, how do you account for whether the color of the galaxy is because of redshift or because of...
No, that's a really good question. We can actually take out the expansion of the universe. We can figure out whether it's moving or not moving because of the shift in the line radiation of the spectra. Okay, so once we take that out, then we can look at the color, and astronomers will say in the rest frame of the galaxy. So as if you were standing in the galaxy, now you're looking at the galaxy, is it red or is it blue? Well, it's not that red is hotter, it's actually the opposite. Red is cooler. So red stars tend to be old stars that are cooler stars. Blue stars are young stars that are very hot. So if you look at the sky, for example, I think you can see it here. If you can see Orion.
Yeah.
Orion Nebula, the Orion constellation has two stars on the opposite end. One is a red star.
One is blue.
And one's blue. The blue one is young and hot. The red one is old and coldish. In fact, big and cold. One day, that one's supposed to die. It could be tomorrow or it could be next week, or 10 years from now or 100 years from now. But the blue one is the young one.
Secondly, in your simulation, do you consider dark matter?
Yes, we do. I deliberately avoided dealing with dark matter, but yes, we do. It turns out that, I mentioned matter in the universe. And I said that there's, we are made of ordinary matter. We heat up, we cool down, we radiate. Ordinary matter has pressure, or ordinary matter is also the kind of matter that you have in the swimming pool. If you put your hand out of a moving car, I wouldn't recommend that you do this, but if you're in a parking lot, maybe you could do this. You'll feel a wind, and that wind is pushing your hand back. All of that is due to ordinary matter. Ordinary matter only makes up something like 10% of the total matter in the universe. The other large fraction of the matter content of the universe is dark matter. It only responds to gravity. So the first image that I showed you that was gravity only, that was a dark matter only image. But I deliberately avoided talking about that complication because it would need another 20 minutes to explain.
So sir, I had two questions. First of all, sir, as we believe that photons are massless, so how come photons which are massless are trapped by the gravity of black holes?
So photons are massless, but they also have mass energy. And really, they're not being trapped by the gravity, but gravity, what is gravity? In Einstein's theory of gravity, gravity is the curvature of space-time. Right? What we call gravity is really us feeling the curvature of space-time. What a black hole does is it makes the curvature of space-time so steep that even a photon can't get out. It's like climbing up a cliff. You climb up and you basically turn around and fall back in. That's a good image. It's an analogy, okay? Don't take it literally, but it's an analogy, a way to think about it.
So sir, as for example, the Hawking radiation. So sir, Hawking said that anything that goes inside the black hole comes outside as a radiation, but there's no the information of it. So sir, what's your point of view on it? That anything that goes, how does it come outside?
So that's an interesting question. It's a question that caused a lot of controversy for a long time. I'll tell you what the problem is. Yes, Hawking said that a black hole evaporates. So if I throw mass into a black hole mass grows, but then because of Hawking radiation, it evaporates. So in principle, what goes in comes out. But it comes out without information, as you mentioned. But that violates quantum mechanics. Quantum mechanics says you cannot put in information and get zero information coming out. So there's a whole school of people who study black hole physics who try and figure out what's happening. One of the pictures is when you add quantum mechanics to relativity, then you start to find that the region around the black hole where the Hawking radiation comes is actually not a perfect sphere. It's ripples. It's got little fluctuations on it. And that fluctuation changes the Hawking radiation from point to point to point. So somehow the information is coming out, but it's coming out garbled. So as far as nature is concerned, the information is coming out. As far as you and I are concerned, it's so noisy that we can't actually make any use of it.
Good afternoon, sir. One of the best lectures, one of the most stimulating lectures I heard. My question as a biologist is that out of so many multiverses, so many worlds, and so many galaxies which you are observing or you are studying, ultimately, one out of that may be offering some material which is exactly like what is on this planet Earth. What is called as a Fermi's gallium.
Yeah.
And is there anything which you find that it has an equal to that of the life on planet? Because one of the best riddles which a biologist is to find, suppose at the end of this research also, to find out whether the life exists at distant place, Earth runs by
Yes.
what the last one has also said, that the presence of K280b biomarker on this planet is equal to that of the Earth's DNA. So do you feel that out of this one possibility, there are multiple possibilities of having the same ambience as that of this one and the existence of life in a different form? Is DNA a necessity or a biological activity?
Okay. That's an interesting question that I think when I'm with my colleagues, we are